Okay, thank you very much. So welcome to the second of my two seminars on complex and active fluids. Just to start with a reminder of where we got to in yesterday's talk. So I gave a pedagogical introduction to complex fluids and to the study of their deformation and flow, that being rheology. So I introduced their basic flow properties as comprising softness under shear, viscoelasticity, normal stress differences, and the fact that in the steady state flow curve of shear stress as a function of shear rate, generally you have a linear regime at slow flow rates followed by a nonlinear regime at higher flow rates. And then an extreme form of that nonlinearity is that they're easy to drive through flow-induced phase transitions. I then introduced the kind of general structure of continuum models that we use to model the flow properties of these complex fluids, and I focused on one specific example, the reptation reaction model of worm-like micelles, which I focused on in particular because it set me up to go on to the next part, which was considering the fact that these materials quite generically seem to show flow instabilities. And I exemplified that by effectively cranking up through the spatial dimensions, starting off with a homogeneous flow, with the concept of a flow curve, although actually when the flow curve has a funny form like this, I prefer to call it a constitutive curve because it's not the thing that's actually measured in an experiment. And I discussed the fact that the reptation reaction model, but actually a whole class of models in rheology, predicts, for a case of homogeneous flow, so not the banded flow, but the homogeneous flow, predicts that the shear stress as a function of shear rate has a Newtonian regime and then a declining stress as a function of strain rate. And we discussed the fact that that's an initially homogeneous state starting on that negatively sloping part is linearly unstable. And I worked through a linear stability calculation to exemplify the basic tool, which can be used widely across active matter as well. And we found a positive eigenvalue to the growth of fluctuations in this regime. And the eventual state to which it proceeds, which can also be calculated from the model I wrote down yesterday, although I didn't do that, is a coexistence of two bands, a band of high shear rate corresponding to this value here, and a band of low shear rate corresponding to this value here. So that's a one-dimensional state, assuming that the interface between the bands stays flat. And then I showed that actually if you can do another linear stability calculation where you start with a one-dimensional base state and then allow perturbations into two spatial dimensions, and you find that the interface goes unstable to undulations along the interface, though I didn't discuss that in all that too much detail. So the intention there was to give a pedagogical introduction to complex fluids, partly because active dynamics often takes place in the backdrop of a fluid that is itself complex, but also, of course, because active fluids are themselves complex fluids, albeit active complex fluids. And so what I want to do now is try and draw as close a pedagogical parallel as I can between yesterday's talk and the hydrodynamics and rheology of active fluids in today's talk. So after 4 weeks at this school, you need minimal overview. In fact, I probably need more of an overview than you do. But just in a couple of slides, I'll discuss the way that my thinking first got drawn into active fluids. I'll then discuss continuum models, which actually have essentially the same kind of structure that I talked about for complex fluids yesterday. And I'll present the particular continuum model that's then going to set me up to do essentially the same procedure again, to start by constraining at the level of theoretical analysis that the flow remains homogeneous shear, then allowing one-dimensional perturbations that lead to a kind of banding effect, and then looking at what happens when we do full simulations in two spatial dimensions. Okay, so that's part A and part B of the talk, and then depending how we get on time-wise, that will potentially be followed by parts C and D. So part C is really more of a, so I think this style of talk that I'm giving is called at Les Ouches seminars rather than lecture series, so I've taken the liberty of going into more of a seminar style mode of presentation here, where I'll discuss some work that we did in my group focused on this prediction of motility-induced phase separation, which Mike mentioned in his last talk, and discussing actually the possible suppression of that phenomenon by when hydrodynamics are included. And then finally, if there's time, I'll go back into real sort of basic pedagogy and talk a little bit about the numerical models, probably only for the the numerical methods, probably only for the continuum models rather than the particle simulations. The reason I want to do that is not because there's any rocket science there, but actually because for the first couple of years after I was a postdoc starting out as an academic faculty member, there were lots of kinds of questions that I wanted to answer with these kinds of techniques, but I was always felt very daunted by the notion of doing these kind of fluid dynamical continuum simulations, because I thought there was something deeply kind of mysterious and complicated about them. So if nothing else, I'd just like to give you a piece of psychology that really it isn't rocket science, and that that's the kind of techniques that you use are really relatively simple. But we may not get that far. Okay, so let's return to the first part, which is this overview, continuum models, and then cranking up through the spatial dimensions from homogeneous flow to 1 dimension to 2 dimensions. So the introduction is very minimal. So yesterday I talked about this concept of a complex fluid as being a background solvent and mesoscopic substructures, which here I've chosen to draw as rods in a liquid crystal. And we talked about the concept of a phase transition induced in that case by the application of a shear imposed at the system boundaries externally on the system as a whole, and the fact that you can drive the system through an isotropic pneumatic transition by the imposition of a shear. And the reason it's relatively easy to drive these systems into nonlinear states and eventually through phase transitions is that the intrinsic rate of relaxation of these rod-like substructures is very slow compared to the jostling of water molecules, for example, and so the shear rate only needs to exceed the reciprocal of that very long relaxation time before we get into a very strongly nonlinear regime. Now, as we all know, and you know probably far better than I do, in fact, that in these active fluids, we don't necessarily even have to think about driving at the boundary, but actually each of the individual mesoscopic substructures is in itself self-propelled, and I've drawn a sort of deliberately close analogy with the previous slide. So these systems are out of equilibrium from within rather than being driven at the boundaries, but nonetheless can show sort of non-equilibrium ordering transitions, just as in the sheared case. Effects such as swarming, which we've heard a lot about today, spontaneous flows that look like something approaching turbulence, and potentially also activity-induced phase separation. The kind of phenomenon that I want to work up towards in this first part of today's talk, part B of the overall overview, is this notion that even in the absence of shear, you can get spontaneously, due to internal activity, spontaneous flows, which in a bacterial suspension, for example, here's a flow map that looked to have these sort of almost turbulent-like swirls, which on a length scale much larger than anything to do with the individual particles. So we see these kinds of emergent hydrodynamic phenomenon. And that's the kind of thing that I'd like to work up towards through the first part of this talk. All right, so I'm going to do that in the context of continuum models, and if I get onto the second part on motility-induced phase separation, I'm going to switch to particle-based simulations there. Now let's recap what I discussed yesterday about continuum models for passive complex fluids. So the basic idea there is, well, we have an incompressibility condition that the divergence of the velocity v is 0, and then we just have the Navier-Stokes equation. Mass times acceleration is the sum of forces that act. Solvent drag due to velocity gradients with a solvent viscosity eta. Pressure gradients, which can force a fluid from place to place. And then the novel feature in complex fluids is we have an additional stress, which then depends on some mesoscopic substructural variables, which I've denoted in a general way by a tensor W here, and I discussed yesterday in worm-like micelles. That tensor is a local molecular strain variable that tells us how deformed the worm-like micelles are compared to a random walk that they do in their undeformed state. And so the challenge for any theoretical rheologist who wants to derive a constitutive model is first to derive the way in which the viscoelastic stress depends on that variable. I've shown this as though it's local here, but there can also be gradient terms in here. And then the challenge also is to derive an equation of motion for the way in which that mesoscopic variable responds in flow. There's generally then relaxation onto a background undeformed state and things that stir the W variable up by flow effectively and cause stresses because the molecules get strained away from their random walk state by the application of a flow. Right, so what's the structure of continuum models for active fluids? Well, actually, really it's the same, effectively. So we're just now mentally switching from the order parameter being the molecular strain variable W to now being a pneumatic order parameter tensor Q, and then we have an equation of motion for the way that Q behaves in flow. On the next slide, I'm going to show the details of the particular model that I've used for the calculations that I'm going to present in what follows. I don't want to talk in detail through the specific structure. Many of you will have worked with this model far more recently than I have, but there are two things that I want to show really. One is that it ascribes to this overall structure, and the other is for any aficionados in the audience to really just tell you exactly which model I am using. I also must apologise that there have been a couple of changes of notation between here and the next slide. For example, the stress, I've shown this as the divergence of an overall stress, and I've denoted the overall stress by capital sigma. But the overall structure is the same. So first of all, we have a Navier-Stokes equation. The pressure actually has been absorbed into the stress here. This is a solvent term. It's written in index formation. Then there's this stress tensor, which is this object here, depending on Q and its gradients. Ignore the red terms for now. There's then dynamics of that in flow, and all the flow stuff has been actually absorbed into this upper convected time derivative here. And then there's a molecular field that tells you about the relaxation of Q in the absence of flow. I take no credit at all for the derivation of these models. I'll refer you to these authors here. In the absence of these red terms here, this is a model for passive pneumatic hydrodynamics, which you can use to study, for example, the way a liquid crystalline suspension responds to an externally imposed shear flow. So that model has been studied widely in that context. And in fact, this model predicts all kinds of interesting shear banding transitions and instabilities at strong shears. But they're not my focus today. Today I want to think about the effect of activity on this model. And again, these authors here thought about that, and at least at lowest order there are two active terms that appear. This one's relatively unimportant in the sense it just renormalizes this parameter. The main one of importance is the appearance of a zeta Q term on the end of the stress tensor. So this is the active contribution to the stress, and this zeta parameter, the activity parameter, will be an important parameter in the rest of what follows. All right, so this molecular field here prescribes the equilibrium behavior of this order parameter tensor in the absence of flow. And in fact, Mike just talked about this a little in the previous talk, is the fact that you can get an isotropic pneumatic transition depending on the value of this parameter phi here through the interaction of this term here with these terms. So indeed, just to sketch that, for phi is less than 3 in equilibrium without shear and without activity, the system is in an isotropic state, and then in a pneumatic phase for phi greater than 3. And what I plan to do here is to study the hydrodynamics and rheology of this active model in the vicinity of this isotropic pneumatic transition. One further thing just to say, which actually again Mike also just said in the previous talk, is that this activity parameter, depending whether it's negative or positive, we can think of two different kinds of activity. The first, in which any of these substructures effectively draws a flow down along its axis and out along its equator. We'll call that the contractile case, and the extensile case is the opposite. All right, so now we have the model, and we're in a position to ask about its predictions for the active hydrodynamics of these rod-like suspensions. And I'm sure actually many of you will have studied the behavior of models like this in your own research. In fact, the reason I wanted to talk about it here is in particular to draw this close analogy with what we learned yesterday about shear banding in passive fluids, to try to convince you that not only many of the same methods but also some of the same phenomenology crops up. So there are many things that we've already learned about in the passive complex fluids literature that can inform us about how to proceed when we're thinking about active fluids. Right, so first of all, let's think about the flow curves of this model. And in the absence of activity, I'm going to choose a regime of parameters space of this model in which the flow curve without activity looks like this. So Newtonian flow, nothing fancy, just stress linearly related to strain rate. So now what happens when we switch on the activity? Well, there are two different cases according to whether that parameter zeta is positive or negative. In the contractile case, the flow curve that was originally Newtonian develops what's called a yield stress. So what does this mean? This means that I can impose a shear stress, which is a non-zero value, and in the limit of long times, the shear rate has to tend to 0. So there's no flow. The system can support a stress without having to flow at a finite rate. That's not, by the way, to say that it doesn't strain. In fact, you can develop an infinite amount of strain so long as the strain rate at long time tends to 0. So for example, you could have the strain going up as a logarithm of time. The strain rate then goes down as time to the -1, and the long time limit is that the strain rate is 0. So this is kind of interesting, but I guess for a rheologist, in a sense, not that interesting because we already know that many passive complex fluids do this. So mayonnaise does this, for example. Sort of dense suspensions of soft athermal particles do it. Colloidal thermal hard sphere colloids also have a yield stress. So that's kind of interesting, but for a rheologist, not particularly that new. The thing that particularly grabbed my attention to the active fluids literature, actually, as someone with a background in rheology, is what happens in the extensile case, which is this. Actually, I'm being slightly disingenuous because there are also, this branch isn't quite so discontinuous as I'm pretending, but loops back round like this. But for schematic purposes, we have effectively a branch at negative strain rates that intercepts the axis at a positive stress, and the opposite case at positive strain rates. So we can think of this, given that this quantity here is defined as a yield stress, what we have in the extensile case is a negative yield stress. So that's really something that I've never seen, and I just don't think can occur in any passive complex fluid. So I was interested in what that might mean for the flow properties of these active fluids. So what does it mean? Well, let's go back to recap what we talked about yesterday. So just to say that all over again, so in for example, a worm like my cell, we have stress as a function of strain rate that has two branches with an unstable part in between. And so if we impose a shear rate here, say, then we can have a separation into gamma dot low, gamma dot low, gamma dot high, and this is the low shear band, and this is the high shear band. So that's just what we learned yesterday. Now let's draw, by suggestive analogy, the constitutive curve from the board on the right-hand side for the extensile systems. So let's take this constitutive curve, and just as in this case we imposed a shear rate somewhere in this regime here, now let's impose to this active system a shear rate equal to 0. What does imposing a shear rate equal to 0 mean? It means taking your two plates and holding them fixed and doing nothing at all. So does anyone have any offers for what might happen when we impose a shear rate of 0 to this system with a flow curve with these two branches like this? Yes, thank you. Right. So you have a coexistence of gamma dot low, which is gamma dot minus, and an equal and opposite gamma dot plus here. So that will look in the flow profile. So there's gamma dot plus here and gamma dot minus here, and with some interface between the two. So this was the thing that really grabbed my attention, as I say, about active fluids, because we can interpret this instability now as effectively two shear bands forming in a system at 0 imposed strain rate and actually with 0 stress, as forming a superfluid phase in which you have a V-shaped velocity profile with a band of positive shear rate coexisting with a band of negative shear rate. So that's what happens at the level of a one-dimensional calculation. So I've just shown there what I've sketched, in fact, on the board. Now what happens when we impose, so far we've imposed no shear rate to the system. And now what happens when we impose a shear rate? Well, again, we can do this by analogy with what we learned yesterday about shear banding in worm-like my cells. So as I said yesterday, as you track the overall applied shear rate to the system as a whole through this banding regime, the shear stress, which is uniform and therefore common to both the bands, stays constant. So you transit across a plateau here. The shear rate in each band also stays constant, so this stays constant, as does this. And the only thing that adjusts if you move the shear rate from here to here is that eventually you end up with more of the high shear band compared to the low shear band. And so we can see then, if we now take our system and start to shear it, the shear stress is going to stay the same and common to both the bands, as is the shear rate in each band. Let me therefore use a different colour. And the steady state flow curve, at least at the level of this one-dimensional calculation, will have this superfluid window. And so as we track the shear rate from 0 up to something in this regime, as in now if we impose a positive shear rate on the system, the shear rates in each bands will stay the same, the stress will stay at 0, and you will just then have more of the positive shear rate band. And that's indeed what we see. So here I've shown this at the level just of a sketch, I'm now going to show some actual numerical data for the velocity, and whereas the sketch has the y-coordinate across the channel like this, that's the independent coordinate, so that's going to be horizontal, and then you're going to see the velocity profile on the vertical axis. So in other words, things are going to be rotated around like this. So this is the velocity profile, 0 imposed shear, and then you impose increasing values of shear rates, and you just get more of the high shear band until eventually, at a high enough shear rate, the whole of the gap is filled by the high shear band and there's none of the negative shear band left. So, I mean, this is an instability that's been thought about a lot in these systems, but I think the thing that maybe the analogy with complex fluids brings is this understanding of it in the light of how we think about shear bands in complex fluids. All right, so nothing that I've said so far tells us anything about the interface between the bands, but recall yesterday we had this parameter little l in the simple model that I wrote down for the banding case, and that set the width of the interface between the bands in the sense that if you sketch the shear rate as a function of position y across the cell, then it's low here, gamma dot low, and it's high over here, gamma dot high, and in the absence of that parameter little l, there would have to be a step function here. On the other hand, nature doesn't like step functions particularly, so that little l then tells us, and in fact in the simple model that I wrote down yesterday, the interface has a tan shape with a width set by little l. In the case where you have multiple viscoelastic variables coupled together, you can get stuff like little oscillations in the profile in the vicinity of this interface, and you can understand that in terms of dynamical systems theory, but I won't go into all of that. Okay, so there's a slightly diffuse width of the interface here set by this parameter little l of yesterday. Now, in the pneumatic hydrodynamic model that I wrote down, recall I said there were local terms in which Q depends on itself only at some position in space, but there are also spatial gradient terms, and in particular I'm going to think about this spatial gradient term here. This is a sort of Frank constant in liquid crystal theory, and it's in fact the square root of this parameter k that's going to set a microscopic length for the width of the interface in this case here. Yes, hello? What do you? Well, yeah, I guess you do in each band. Yes, I guess you do, and is that's balanced by the input from activity, I suppose. Yeah, is that what you mean? Mm-hmm. Well, okay, no, but zero stress though, isn't it? So yeah, that's right. I've never thought about it in those terms actually, but I guess if you think about the dissipation as some integral of the stress times the strain rate, then actually not. Yeah, perhaps we could discuss that. Yeah, I haven't thought about that sufficiently recently to have a very sensible answer to that. Yeah. Hello. The 1D shear banding stuff, you mean, in the active fluids? This one here. Not that I know of, and the reason for that is actually what I'm going to tell you in a minute, which is that this 1D state is usually so unstable that it then goes on to create more exotic stuff still. Well, say a suspension of swimming bacteria, for example, and people have measured viscosities that are less than the background solvent viscosity, for example, in these bacterial suspensions. I should confess that I'm actually now quite out of date on this active matter literature because I've not really been working in it for the last 2 or 3 years. But oh, have they? Oh, well, that's good to know, actually. Right. Did they somehow reduce the dimensionality? Sorry, my earpiece has just gone wrong. Did they reduce the dimensionality of the system in some way? Or? Right. Ah, okay. So, right. Yeah. But they're averaging over stuff that's more complicated in the second dimension. That's what I would have expected. Yeah, okay. Yeah, thanks for that. Yeah. Um, right, so yeah, so what I was saying there was that the interface between the bands here has a slightly diffuse width set by that parameter little l that was in the model yesterday. And in this model here, we have this Frank free energy constant here, and the square root of that is going to set the width of this interface here between the equal and opposite bands. So having shown the velocity profile here, I'm going to now differentiate it to get the shear rate profile to show you a bit more explicitly what that interface looks like. I must also make an apology because actually I'm showing data for the same system but just from different runs, and actually in this case, in the velocity profile shown here, the negative shear rate is at the left and the positive at the right. Of course, you could have the symmetry broken in the other way just from tiny perturbations in the initial condition, and in the graph that I'm going to show you on the next page, the positive shear rate is on the left hand side. But so here's the shear rate as a function of position across the gap, and this is for a rather small value of that parameter little l set by the Frank-Friengi constant. Yeah, hello. I don't know. Yeah. Right. No, it's been divided by a modulus and then taken the square root of. Yeah. So I set the modulus to 1, and I've done that here again today. So, there's something of units of modulus in this model here, right? So maybe the modulus has already been set to 1 here. But there's a scale of stress that's intrinsic to the local piece, and then there's another scale of stress from the non-local piece. This is dredging up my memory here. So if you take the non-local piece and divide it by the scale of stress inherent to the local stuff, and then take the square root, that then gives you something that has units of a length, and that's the thing that I'm converting into a length. Yeah, right, so that would have the, yeah. I'm just struggling a bit for where the modulus is in all this part, in these local bits here, isn't it? Where? Oh, it's in the, it's in here, is it? Yeah, it's in here, right. Yeah. Yes, okay, so there's a modulus in H that's been set to 1, yes. Yeah. It's not set by, right, so there's a modulus in here that's been set to 1, and I'm just defining a quantity, which is this quantity here divided by this modulus, which has been implicitly set to 1. That then gives you something that is a length squared, and I'm taking the square root of that. It is. Yeah, that's right. Yes, I get, yes, right, yes, I guess, yeah, yes, it is, yeah. Okay. Right, so yeah, so this has been divided by a modulus and taken the square root of, and that gives you this parameter little l, which is effectively the analogue of our parameter little l from yesterday. And for small values of that little l, the interface is relatively sharp compared to the box size, and we had a nice discussion of diffusive lengths compared to box sizes this morning. And then as you take that diffusive interfacial width to be larger, what you have initially is simply the values in the more or less still bulk bands as before, but with a more diffuse interface between the two. And then as that interface width becomes of order the box size, you not only get a much broader interface still, but actually you start to iron out the spontaneous flow altogether until you wipe it out beyond a critical value of the length. Therefore, and all of that I said, all of this that's presented here is for fixed activity and for increasing values of little l going this way. So in other words, for fixed value of the activity, for low values of little l, you will have spontaneous flow, and then they will be ironed out to nothingness in these open symbols here. And then what you can show by exploring that phase diagram in more detail is that in the plane of activity and the activity parameter normalized by the passive modulus g and this length scale that we've already talked about, then there's a phase boundary between the two which has a slope of a half. So no flow up here and spontaneous banded flow in this regime here. Alright, so that's allowing only spatial variations in one spatial dimension, that is taking two plates and normal, allowing spatial variations in the direction normal between the plates. The obvious question then, and we explored this yesterday in the context of the shear banding systems, is to say, well, now in the finest tradition of a hydrodynamic stability calculation, let's go up another dimension and take this one-dimensional state as a base state and add to it two-dimensional perturbations and ask about the fate of those. And in fact, the way I did this was not by doing a linear stability analysis, but just the sort of brute force method of putting those equations, the hideous slide of equations in index format, onto the computer and solving it effectively with the techniques of direct numerical simulation as a fluid dynamicist would do. So I'm doing that in a two-dimensional plane with periodic boundary conditions in this direction and closed plates in this direction. So now let's talk about that. So what do we find? So here's this same phase diagram that I just talked about before, and this is the phase boundary that I just discussed, below which in the one-dimensional case you get spontaneous bands forming, and above which you don't have any spontaneous flow. So now I do a simulation in which I take as my initial condition, for a 2D simulation, this one-dimensional banded state plus tiny perturbations which have structure in this second spatial dimension, and I just shut my eyes and I was going to say shut my eyes and watch it go, but that's not going to work, is it? Just watch it go. Right, so what happens if you're in the regime where there's no spontaneous flow in one dimension? Well, in fact, we still get no flow even in 2 dimensions. That doesn't rule out there being a nonlinear instability to finite amplitude perturbations, but I didn't look into that. But this is kind of an expensive simulation to do to see that nothing happens, but nothing did happen. In the regime where in the one-dimensional case we have these 1D shear bands, we find that those always destabilize to these two-dimensional perturbations to that, initially of small amplitude, are always unstable and grow and take us away from this one-dimensional state to a more complicated state. And depending how far we are over this borderline of instability, we can find 3 different kinds of states. One in which the state that's eventually reached at long times is time independent. Another in these hatched symbols here, the more densely hatched symbols, in where the state is oscillatory in time. And another further over here by the solid symbols, in which it's quasi-chaotic. It may indeed be chaotic. I'm just saying quasi to hedge my bets because I didn't calculate a Lyapunov exponent formally to show that it's chaotic. So let me now show you some of those states. And I'm going to show you snapshots of a state on the ultimate attractor for 6 different values of the activity parameter zeta, going from relatively less active to relatively more active for some fixed value of this interfacial width little l. So let me do that on the next slide. So here are the states. On the left is a grayscale of one of the components of the Q tensor, and on the right are the associated velocity vectors, which haven't really shown up very well at this length of the velocity vectors, but I hope it shows you somehow swirling flows. So what do we find? When we're just over the boundary into instability, the one-dimensional banded state breaks up and forms something at long times that look a little bit like Bénard convection rolls for anyone from the conventional fluids community. So that's this effect where you take a slab of fluid between plates and have a differential temperature gradient, a higher temperature below. The fluid at the bottom expands. It wants to move upwards, but because of incompressibility it can't all move up, so you get plumes that move up and recirculate back around. So this looks a little bit like that. And then these rolls somehow break up into something that's a little bit more swirly, but still nonetheless time independent. They then become oscillatory, and finally you get something that really looks like a chaos in any scalar signal that you measure, and where you have this very kind of turbulent-like, chaotic-like, again hedging my bets about whether it's really either of those things, at long times. So the obvious thing to try and characterize here is some sort of length scale associated with these swirls. And just by visual inspection, we can see up here that that length scale looks to be about the box size, and then it looks to be decoupling from the box to become smaller and smaller with increasing activity. So what we did then in a later simulation, and this was a collaboration actually with Cristina Marchetti at Syracuse, is to calculate the relevant length scales, and we did that in 2 ways, one of which is the spacing between these defects, and the other is the correlation length in the orientation of the Q tensor. And we plotted those as a function of this activity. So again, we can get into a twist with dimensions here. This activity parameter is the value of zeta normalized by the local modulus G, which is there in that molecular field. And these are length scales as measured from the simulation, normalized by the microscopic length little l that I was talking about a moment ago. And what we find in the limit of low activity is a saturation, and this is the regime in which these swirls. So actually I should say that there's a switch here now. We're doing biperiodic simulations here, not closed simulations. Here we have swirls that are bumping into the box size effectively, so we've got like a saturation effect going on. And then as we go deeper into the unstable regime, we see an ever decreasing length scale, and both of these lengths seem to scale in the same way with increasing activity, which is as a -1/2 power. And the same has also been seen, by the way, and appeared in press a little bit before ours by Luca Giomi in his work with Mahadevan. Hello. This length scale? Well, it emerges out of the dynamics. What do you mean? Oh, I see. Well, okay, I guess it's a competition between activity and the restoring frank free energy. Do I have a better explanation than that? Yeah, I think that's what I would say for that.
Is there any relation to the spectrum of the unstable mode?
That's a good question. Do you mean the dispersion relation of the unstable modes? I can't remember, and I don't think we looked at that, actually. Yeah. I should say, by the way, one thing that we never did, and I'd be interested to know the answer to this, but I'm probably not going to calculate it. I didn't say yesterday, but the instability that takes this state from being one-dimensional into 2 dimensions is that what you have across the interface between the bands is a jump in the normal stress between the bands, and it's the fact that you have a jump in the normal stress from one state to the other that means that if you have anywhere a slight tilt in the interface, that tends to get more pronounced as a function of time. So I would call that an interfacial mode of instability, in the sense that you only have the instability because you have an interface between the 2 bands. One question I thought about a number of times, but we somehow never really pursued in this case, is whether this instability to 2D is fundamentally because you have this one-dimensional interface, or whether it's somehow a property of the bulk phases itself. Someone in the room may know the answer to that question. I suspect it's because you've got this interface, but I don't really want to say more about that. I guess I never in these systems in flow, I never particularly think about energy minimization. Maybe you do, but it's not the way I tend to think about it. But, yeah. Okay, so what we did yesterday, just to recall, was we modelled the flow properties of complex fluids by having a viscoelastic stress, which had its own equation of motion, and that was for some polymeric stuff. It happened to be a worm like my cell, but there was a molecular strain tensor W, which had its own dynamics, which could either be reptation reaction, and then I showed you some results actually for a closely related but more phenomenological model called Johnson-Zagerman, and we saw banding and instability of the interface. What we've done here is a very similar model, but with activity and for this Q tensor, but this is for a suspension of active rods in the backdrop of a fluid that is itself a rheologically simple fluid. So we have active rods suspended in a Newtonian solvent. You could, of course, ask, well, and in fact, one of the motivations for me saying that it was interesting to learn a bit about complex fluids for people in your community working on active fluids is that activity often takes place in the backdrop of a fluid that is itself complex. So how do we think about that? And I'm not going to go into details here, but I just want to draw your attention to the fact that it can be done and has recently been done, is you can say, well, now let's take a system in which we not only have the active rods that I've just been talking about with the dynamics with that d by dt of q alpha beta on that very complicated slide, we can also take an additional stress, which is now due to a background polymeric fluid. So we have a suspension of active rods in the background of a passive polymeric fluid, and then that can obey its own dynamics, which we can choose to be a well-known polymer constitutive model. Again, we've used the Johnson-Zagerman model, and this model then really combines the rheology of a passive background polymeric fluid with the dynamics of an active pneumatic. I'm not going to go into details, but just to say that that's in those papers there for anyone who wants to have a look at them. And some one example of the kinds of effects that we saw there. Actually, once you have a background polymeric fluid with a viscoelastic relaxation timescale, you're at liberty to say, well, I can set that relaxation timescale to infinity if I want to. Then you don't have a background polymeric fluid, you have a background elastomer. And that would be a problem, I guess, if you were thinking about imposing a shear flow from the outside, because you'd be indefinitely shearing an elastic solid. But if you've hello. But you've just got effectively local activity, local swirls in the backdrop of an elastic solid. And what we see, one example of the kinds of effects we see there is a very, very slow coarsening phenomenon, where at early times you have these swirls that are features of the active Q sector of the dynamics, and then as time goes on, it gradually realizes there's the polymer in the background, and so everything gets ironed out. So you have a coarsening dynamics there, and you can calculate a coarsening exponent and so on. In the limit of very long times, those swirls get more or less effectively ironed out. I'm not going to say any more about that. If you want to have a look, you can have a look in those papers there. All right, I'm now going to switch gear a little bit and move away from, so what we've done in both of these first two sections, first on complex fluids and then on active complex fluids. Hello? Yeah. Oh. There's no external shear imposed here, actually, but yeah. Say the question again. I'm sorry, I didn't understand the question. The flow profile for this kind of system? Actually, that's really annoying because I just deleted a slide that would have said something about that because I thought it was a bit too much to go into. For a finite value of the polymer relaxation time, you can ask what is... Well, one question that you can ask is whether when this one-dimensional banded state here, which clearly has a net throughput, now that this symmetry is spontaneously broken, so there's nothing to say that at very long time intervals there may be a left-right switching so that the throughput then goes the other way, but at any time there is nonetheless a non-zero throughput. Now, when you've broken up into these two-dimensional states and integrate over it to ask whether there's a net throughput, in some of the states there is and in some of the states that there isn't. One of the things that we found when we added this polymer in is that has a dramatic effect of hugely increasing the regime of the phase diagram in which you have a net throughput. So I think what that would mean is if you did the integral to find, as you were just saying up there, they've done in these experiments, effectively integrate over the second dimension to find the one-dimensional flow profile, that the effect of adding in polymer would be to tend to make the one-dimensional flow profile to have a throughput, whereas in the absence of polymer you tend in the two-dimensional states often to get no throughput. But I don't have anything more intelligent to say about that than that. Yeah. Okay, any further questions before we switch gear into the... All right. Okay, so in the first two sections, I've assumed, so in this first section here, we talked about polymeric-like fluids or worm-like micelles. We could have thought about colloids or any other complex fluid. And we assumed, actually it's not always the case, but we assumed that the concentration field remained uniform throughout. So the concentration of polymer chains relative to the solvent was uniform everywhere in the cell. Actually, in many shear-banded systems, that's not the case, and the flow and the concentration dynamics get coupled together, and so the formation of shear bands tends to lead to a slight phase separation in the concentration field as well, but I won't go into that. I've assumed that the concentration field also of these active rods remains constant in time and space. So that's one difference, and the other is that everything here has been within continuum models. What I'm going to do now is explicitly address the possibility of a phase separation where the active particles pile up in some region of space, leaving depleted solvent in the other part. And the other thing is that I'm going to switch methods, that's just a detail in a way, from continuum models to particle simulations, about which I should say I know vastly less than I do about continuum simulations. But I'm ever keen to learn more. All right, so let's do that now. So the basic phenomenon that I'm going to be concerned with here is the phenomenon that Mike just mentioned in the earlier talk and that he's worked on very extensively with Julien Tailleur, which is the possibility in an active system, even in a suspension of hard sphere particles, if they're active, there's a possibility of them undergoing a phase separation induced purely by the activity. So nothing to do with any sort of potential interaction between the particles leading to phase separation. So that possibility is out there and in the literature, and there are many lovely papers by Mike and Julien on that. On the other hand, what those papers don't have is the inclusion of hydrodynamics between the particles. And what I wanted to do was, in fact, and this came out of a conversation that I had with Mike about hydrodynamics, was look at the effect of hydrodynamic interactions on this effect. Because I'd written some simulations of active particles with hydrodynamics and showed Mike some snapshots, and we were discussing over the phone, and he said, well, why on earth isn't this phase separated? So that then persuaded me to think a little bit more about why it wasn't phase separated. So let's first of all recap the mechanism for motility-induced phase separation. And we're going to do this in the context of these so-called run and tumble particles. So what we've got here are hard sphere particles in a background solvent with some volume fraction phi. And the dynamics of any particle is that it runs in a straight line at some speed v, and then intermittently it will tumble. These tumbling events are fast. And the intervals between them are stochastic, but the intervals are chosen with a characteristic event rate 1 over tau 0. I should apologise that some of these texts have got a bit offset from one line to the next. That's just because I'm now using a different version of PowerPoint and it's somehow messed everything about, but I don't think it's too bad. So that's the system. And the effect that Mike and Julien discussed, positive feedback effect, is that these particles will tend to accumulate, as in, therefore, the local volume fraction will go up in any regions where they slow down, where the velocity is lower. So that's a sort of nice intuitive effect, and you can think maybe about the analogy that's often discussed, I think, is window shoppers on a high street. If there's a particularly interesting window, people move more slowly past it, and you tend to get people clustered there. So that's intuitive, but it's inherently a non-equilibrium effect, because in an equilibrium colloid, for example, you wouldn't have the local concentration depending on any mobility constants. So that's the first part of the loop. And then the second thing is to say that in regions where they've become crowded, they must slow down because they have to somehow jostle and fight their way past each other. So this gives a very natural positive feedback. Particles accumulate where they slow down, and particles slow down where they accumulate. Positive feedback should give a runaway instability. And the spinodal condition that's in this paper here is when the logarithmic derivative of velocity compared to volume fraction is less than -1, there should be a spinodal instability whereby an initially homogeneous suspension where these particles are distributed uniformly throughout the solvent, where they should then start to phase separate so that you have more particles in one region and relatively less in the other compared to the solvent. So that was a pen and paper prediction. It was then verified in numerical simulations. The left-hand side here is indeed run and tumble dynamics, albeit on a lattice, so I don't know the details of how that was latified, but nonetheless it was. This again was from the Edinburgh group in days when Mike was there. And you see here domains of phase-separated particles. So that's in the run and tumble system. Cristina Marchetti's group then looked at this actually in a slightly different system. So what we had in the previous system was run and excluded volume, so the hard spheres can't overlap each other, and intermittent order 1 tumbles. So straight line and then suddenly and then straight line again. The angular dynamics in this case are different in that it's not straight line, then order 1 tumble and then straight line again. Rather it's a continuous stochastic switching of your angle with some rotational diffusion coefficient. These simulations are usually called Brownian in the literature. I think by that they don't mean Brownian in the traditional thermal sense of the term, in which there's therefore also a translational diffusion coefficient there, but Brownian in the sense that the dynamics of whatever micro bugs are swimming around, they're constantly switching their angle as they go around in space. But nonetheless, there's a characteristic rotational diffusion time which we can somehow think as something analogous to the intermittent switching time in the run and tumble. And these investigators also saw phase separation, as you can see in this simulation here. So this is a snapshot taken from their paper. In neither case, however, is hydrodynamic interactions between the particles included. And so what I wanted to ask is, what effect will hydrodynamic interactions have on this effect? So to do that, I needed a model of hydrodynamic swimmers, for which I take no credit at all. This is a model that Tim Pedley and co-authors have thought about for a long time, but actually dates back to Blake in the 70s. So this is a suspension of hard, I would like to say hard spheres in 3 dimensions. It's actually hard disks in 2 dimensions. You will therefore be starting to worry about Stokes catastrophes, and I'll make some comments about that in a moment. So hard disks in 2 dimensions. Stokes solvent here, incompressible Stokes solvent. You've seen the equation for Stokes equation before. And around each disk, so these particles swim by squirming. So the model there might be a model of a bug with lots of cilia around the edge, and it can waft its cilia. And if you integrate over that layer of cilia, there's effectively a slip velocity around the edge of the particle, and it's this wafting that creates an apparent slip that causes the propulsion. So that slip could have, in general, many Fourier modes around the edge of the disks, but we're only going to take here the first 2. And in fact, if you just have one disk then in isolation in a solvent, it has a free swim speed given by b1/2 in an instantaneous direction alpha1. And what we can do then is a simulation in which at any time step we ask what forces need to be imposed around the edges of these disks in order to give us these squirming velocities. And we do that by exactly solving Stokes' equation in this regime here, subject to those forces that give us these velocities. That then and that, I should say, fully captures far-field power law propagators between these particles, and also, once we've converged on any mode numbers in the simulation, also captures near-field lubrication effects. The output at any time step is the rate of change of the centre of mass position and also the angular velocity. So we can therefore update the angles and the positions of the particles and step forward in time. And yeah. Well, I haven't really told you. So right, so what we do in the simulation is so you have Stokes' equation in the plane, and then around each disk you impose forces that you decompose into Fourier modes. Fourier mode 1, 2, but also 3, 4, 5, 6, and so on. You derive an equation of motion for how the Fourier modes in derive an instantaneous equation for how the Fourier modes in force relate to the Fourier modes in velocity. They're related by a matrix. Now, there are some things that you know and there are some things you don't know. The things that you know in velocity are the higher Fourier modes, but you don't know the low modes, which tell you the centre of mass motion and angular rotation. In the force, you know the low modes, because that's that these swimmers must be torque and force free, but you don't know the high modes. They're the things that you need to impose in order to affect this stuff. Right. So actually what this is effectively a very ancient... So I derived this from scratch in 2 dimensions and then declared myself a genius at the end, and I thought, hooray, I've invented this fantastic method. Turns out I'm an idiot, because actually this is all out there in the literature, and this is an ancient 2-dimensional antecedent of Stokesian dynamics, which has been pursued a lot by John Brady's group, for example, and he's recently adapted it to account for swimming. But what this is, and there are all kinds of clever tricks in his method by putting in analytical forms for far field and near field and all that kind of stuff. And so his now runs very fast, n log n, I think I can't remember. But this method that I wrote down is just order n cubed. Does that answer your question? Baffled into silence. Okay. Right. Okay. No, well, if there's one squirmer on its own, it doesn't. No, you're right. But once 2 squirmers come near each other, in fact, there's a paper by Tim Pedley. They have to scatter off each other, so there is rotation then. Yeah. Yeah. No, that's a good question. Thank you. So yeah. So what this captures then is the swimming of each particle when it's on its own, and then when particles come together, they have to somehow slither around each other, and they can't touch because there's a lubrication disaster as they get closer together. Right. So that's the model of hydrodynamic swimming. So now let's compare the two models, because I want to understand what's going on in this one compared to what was going on in the other one. I'm going to choose to use the Brownian, not the run and tumble, but there's a nice series of papers by Mike and Julien effectively rederiving their run and tumble results for the Brownian and showing that you get the same kinds of effects. So in each of these models there are 6 parameters. There's the number of particles, there's the disk radius, the box size, the Stokes velocity in the squirming case. There's, if we go back to, there's the, this is actually an inverse drag coefficient, slightly odd notation. There's the inverse drag, which is kind of an analogy to the viscosity here. There's the free swim speed, which is just imposed in this Brownian, quotes Brownian simulation, the run speed. Similarly, in the squirming, the run speed is imposed by the value B1. And in the squirming case, there's the relative value of B2 and B1. That gives you either a pusher or a puller. I'm just going to tell you that we've checked that everything I'm about to say applies across the whole range of B1 over B2, so that's not an important parameter. A parameter that will be very important, though, is the fact that in these Brownian simulations you can set by fiat at the output of your simulation what you want to be this Brownian angular rotation rate for the particles changing their angle as they swim along, and that's going to be very important. Alright, so we've got 6 parameters in each, and as I said, the method that I derived for the squirming particles goes as n cubed, so we can only do a modest number. We have checked against 512 and 700 even, I think. I'm going to set it to 256 here. And just to be fair, although we could do many orders of magnitude more, I'm going to set the Brownian one to 256 as well, just to get comparable results. So that means we've got 5 parameters, having a limited one just by computational demand. 5 parameters, of course, means 3 because you can choose units of mass, length and time. So I'm going to choose units of length that the disk radius is 1, of time such that then the swim speed is 1, and of mass such that the viscosity and the drag are equal to 1. So we're only left with 2 parameters in each case, dimensionless parameters. We have the area fraction in each case, which I'm going to explore fully from dilute to close packed. We have this parameter that isn't very important, beta, for this particular phenomenon in the squirming case. And in the active Brownian case, now I had a little moment of mental lapse when I defined this, and I had this funny square rooty thing in front of it. I wish now I hadn't included that. I have. That will give us a slightly peculiar shape to a curve later on, but anyway. So what this tau 0 is the reorientation time that you impose in your Brownian dynamics algorithm. Yeah, I'll come to you in a moment. And that tells us how long it takes to change your angle by order 1 on these Brownian stochastic dynamics. There's another parameter which you aren't at liberty to impose by a fiat in the calculation, but which you can estimate on the basis of mean free path scattering, and that's the typical time in between collisions of 2 particles at any given volume fraction. And I'm going to define a dimensionless parameter, which is called zeta. Again, I'm sorry, it's not the zeta in the last part of the talk. It's a new parameter zeta, which is the ratio of those, and that if that's large, that says that particles collide many times in between reorienting their angle by 1. Yes? Mu. Yeah. No, it wasn't. It's just here. Yeah. Okay. All right. So I'm going to explore the area fraction in each case. All the results that I'm going to show here are for beta is 0, but we've checked a full range, and that nothing depends on that. But this parameter, which sets the timescale, the ratio of the timescales between an order 1 reorientation and bumping into something else, will be important. Right, so first of all, I wanted to reproduce the effect that were being seen in the Brownian dynamics simulation of the Marchetti group. They had about 10 to the 4 or 5 particles. Here I've got a princely 256, but nonetheless. So what's shown here is the measured particle speed as a function of the area fraction. And it has this decreasing curve here, and the Tailleur-Cates spinodal, where the logarithmic derivative of this goes below -1, is this point here. So we should expect spinodal instability in this regime. I don't know that it's been discussed, maybe Julianne could enlighten me, but I guess there would also be a binodal regime here, but you've not, have you published stuff on that? Or yeah, okay, so then a binodal regime here. This measure here is a measure of the number fluctuations in the cell. It gets suppressed at high area fractions just by packing, but if it rises relative to 1, then that's suggestive that there are large number fluctuations, which somehow indicates phase separation. It's more convincing that rise there, seen in the context of that never being above 1, but I don't want to give that slide away too much. So this is indicative of some sort of separation going on. And what we see in the snapshots here, so I hesitate really to properly claim a phase separation with 256 particles. Actually, maybe Dan, could you tell me, in the earlier days of phase separation in the particle simulation literature when computers were basic, how many particles were used to claim phase separation generally? Oh, 32. Ah, great. Okay, I feel sophisticated now. Right, so I claim phase separation, therefore. So these are the snapshots that show some sort of phase separation effect. Now there's a parameter, so we've explored the full range of phi here, and there's one value of zeta here. Remember, zeta, not the zeta from the earlier part of the talk, zeta is this parameter that tells us the ratio between the time to reorient and the time to bump into something else. And as I said, I had this lapse when I was defining it and had this square root, which I wish I hadn't. It's that gives us this, but doesn't matter too much at low volume fractions. So this is the reorientation time, and this is the collision time. And as you can see, a particle collides many times before it with other particles before it reorients its angle in these Brownian simulations, and that you're just at liberty to impose that because the Brownian angular dynamics don't know about the collisions in this case. Right, so that therefore with this large value of zeta, that reproduces what Marchetti was seeing in the sense of this phase separation with 256 particles. Now what happens with hydrodynamics? This. So the particle speed measured in the simulations as a function of area fraction is decreasing here. This is the Tailleur-Kate spinodal. And so we should expect a spinodal instability here and binodal regime here. What do we see? So here's the number fluctuation parameter, which if it were greater than 1 would suggest some sort of separation and gets suppressed by packing at high volume fractions. So as you can see, it never seems to rise above 1. So let's just compare it again with this one before, which rose above 1. It never does rise above 1. And these snapshots really show no evidence, at least to my eyes, of phase separation. It may have some slight string-like structure, but nothing that looks like a sort of translational phase separation. So why is this? So that was a puzzle to me. And what I'm going to work towards, I've effectively given the game away, I think, by telling you that this quantity of the reorientation time ratioed with the collision time is important. So if we think about so in the Brownian case, as I've said, you're completely at liberty to impose whatever reorientation time you want. The collision time emerges out of mean free path considerations effectively, but you can impose whatever reorientation time you want. In this squirming case here, it's done athermally, and there's no angular diffusion due to thermal effects or anything. But the only reorientation that happens then here, but that must happen, is that whenever two particles come together and collide, they have to scatter off each other because of these lubrication effects. That was an effect there in the original paper by Tim Pedley. So in other words, there is no way of imposing that ratio from the outside. You're not at liberty to say what it is. And in fact, because every time two particles collide, they also reorient in scattering, that ratio is always about 1. So that's just an argument, and then we measured here from the simulations what the scatter time and the reorientation time are, and you see indeed the ratio is always about 1. So that's a possible explanation of the absence of phase separation, yes.
What you could do instead, I think, is just to look at the scattering statistics of two particles, right? And then try to infer from that the behavior on a large scale by using a theoretical approach like Boltzmann approach.
I could. Yes. Thank you. Yes, thank you. So that would involve what? Deriving a sort of continuum set of equations for, yeah?
You measure the collision statistics,
right.
Which you can do at the scale
Mm-hmm.
simulated because that's low number of particles.
Right. Oh, and then feed it back into something that looks like a Brownian
Then you
simulation, you
use
mean?
the Boltzmann approach where you have the
Okay.
statistic as input.
Oh, I see what you're saying.
Then you
Right.
derive a field theory from that,
Okay.
and then maybe that field theory
Right.
about the phase behavior.
Well, I wonder if in a very Mickey Mouse way what I'm about to show you maybe is something along those lines, because actually what we did, maybe it's not, I don't know, but what we then did, oh, well, first, that will come on the slide in a minute. Let me, hello? Yeah?
The VFI that you're
Yeah.
plotting here is the particle, the total velocity field along your initial particle. So
It's the particle speed, average particle speed.
okay, so not projected.
No, not projected along your local axis alpha. Yeah, no, not from memory, it's not, no. All right, so why don't we get phase separation? Then I'll show the slide that maybe addresses what you've just said there. So let's revisit the mechanism for why we should have had MIPS in the first place. So there's a suspension of hard sphere particles with some volume fraction. They run with a constant speed. Well, they run, sorry. Yeah. In between reorientation events, they run at some speed v. They then tumble, order 1 change their angle quickly, but with a characteristic inter-tumble time tau 0. And then the feedback mechanism, just to recap, says that they accumulate where they slow down, but they also must slow down where they're crowded, v is v of phi, because they have to somehow jostle past each other, and that's then a positive feedback mechanism. So, however, there is somehow an implicit mean field assumption in here, at least to my mind, is that to experience this decreasing v of phi during runs, they must be impeded during a run, so they must collide many times in order to experience that impeded v of phi, so in other words that v which is a decreasing function of phi. So in other words, they must collide many times between tumbles or between a reorientation within one reorientation time in the Brownian case. So tau 0 must be greater than tau c, so the parameter zeta in the Brownian simulations must be much greater than 1. So that, on the other hand, the hydrodynamic system always has that ratio to be about 1. The feedback mechanism breaks down, therefore, and no phase separation. That's just an argument. Now let's try and back that up by going back to the Brownian simulations, so-called. And the red lines here are just the ones I showed before, where we saw these enhanced number fluctuations with a large value of zeta. Now let's impose a value of zeta that is suggested by the hydrodynamic simulation, and I'm not sure if this is a bit in the spirit of what Erwan was just suggesting there. So we're imposing that to be 1, and indeed you can see here now in the black lines that that ratio, at least in the high area fractions where we might expect phase separation, I'm sorry about this square rooty thing here, is always about 1. And what you can see is no enhanced number fluctuations, and in the snapshots, no apparent phase separation. So that's somehow consistent with the fact that in this hydrodynamic squirming case, we didn't see phase separation. So to summarize this part of the talk then, we've discussed the the fact that motility-induced phase separation is predicted to arise generically in active matter, but it may be suppressed in systems where hydrodynamics is important, so in bioswimmers, for example. We've suggested that the mechanism of suppression is concerned with the fact that the reorientation and the scattering time have to be about the same in these squirmers. I've not said anything here about the effects of interparticle attractions. In particular, if you have a Leonard-Jones interaction, then in the passive case you're going to have all kinds of phase separation phenomena anyway, and so you can then get some sort of interplay between those two. And I'm not going to say anything about that. In fact, I actually can't now remember very much about it, but if you want to read about it, it's all in this paper here. So that closes that part of the talk. Are there any questions about this before I move on? Yes, hello. Oh, yeah, sorry, that was a promise that I never carried out on, yeah. All right, so the Stokes paradox is as follows. So if you take a sphere and drag it through a 3D fluid, everything's well behaved. You can calculate the drag as a function of the velocity and so on. If you take a cylinder in 2D, which is basically what we have, because this is just 2D simulations, and drag it with a force monopole through a 2D fluid, then there's all kinds of disasters there. The drag knows about how big the box is, you get logarithmic divergences and so on. So that's called Stokes paradox. However, that should be a worry in this case, and maybe still is, but I didn't have the resources to do the 3D case. But there are two arguments for why I think it may not be a problem. The first is that we don't here have a monopole, we're not picking something up and dragging it with a monopole force. There's a dipole force, and the reason that the Stokes paradox exists is because there are power laws which are non-integrable effectively. But if you move from having a monopole to a dipole, the power laws are down by a power law of 1, a more rapid decay, and so everything then goes back to being integrable even for a single particle. Now, whether having many particles creates more or less of a problem is not clear to me. Maybe more because there are just more of them and they could cooperate, but maybe less of a problem in the sense that there are many pointing every which way. And I guess a further part of the defense is that actually, if you think about a polymer model in a way, locally you've got, force-free things, and it's very common to do hydrodynamic simulations in 2D. Yeah. So those are my defences, but I should say actually Ignacio Pagano-Barraga has been doing simulations in 3D in the last few years. Yes. Okay. Okay. All right. Mm-hmm. Mm-hmm. Mm. Ah. All right. Okay. Thank you for that. Yeah. Thanks very much for that. Any further questions before I move on? Mm. We did. In fact, we published this together, right? So yes. Yeah. Thanks for that. Any more questions? Okay. I'm just debating now what to do in the fight. There's 20 more minutes roughly. Is that right? So what I could either do, so as I said originally at the start of the talk, everything that I said about complex fluids, which I then drew on analogy for active fluids, was in shear. The other fundamental class of deformation is extension, and I could talk about some work on instabilities and extension in complex fluids that will then have an analogy, may then have some analogy in active fluids, which has not yet been explored. So if I start that now, I could probably more or less get through a fairly coherent picture of that. On the other hand, I could spend maybe 5 or 10 minutes first talking about numerical methods for these continuum models, and then that will mean a slightly truncated version of the extensional stuff. So does anyone have an opinion on that? Would you like to hear about the numerical methods, or do you prefer a more coherent story? Any votes from the audience, or I'll ask Julianne to give a decision on that. You'd like to hear the numerical methods? Okay, all right. So as I said, there's what I'm about to discuss here. There's no particular rocket science. And really, that's what I want to convince you. So I hope this is as much an exercise in psychology as it is in science, because, as I say, I hesitated for a long time after becoming a faculty member as to start actually doing these fluid dynamical direct numerical simulations, because I thought it was this big dark art and I'd never be able to do it. It's actually, once you really get into it and think about it and do it in a methodical way, it really isn't so difficult. And actually, I think quite a large fraction now of the active matter community is doing this. But nonetheless, I hope what I'm about to say may be of use to some of you who are feeling a bit queasy about diving in, which is pretty much what I feel at the moment about more particle simulation stuff. But I've been taking first steps recently, as you've just heard. All right, so let's recap the equation set that needs to be solved. So there are two parts to it. One is that we have Stokes force balance. So this is the Stokes equation with an extra stress, effectively, and incompressibility. And then we have a viscoelastic constitutive equation, which, normally you'd write the stresses depending on some variable and then write down how that variable behaves, but often the stress is just linearly related to that variable, so this is a slight short circuit through that. And then actually for both the active and the complex fluids that I've talked about, this equation has a fairly common structure, at least from the viewpoint of numerics. One is that this is this Galilean term, which says you can either think about the time derivative at a point sitting fixed in space, or you can think about the time derivative suffered by a fluid element as it moves through space. So that has to be there to impose that Galilean invariance. There are these spatial gradient terms, which in a liquid crystal case are like Frank free energy terms. Here they're the terms that set the diffusivity of the polymer stress in the banding case. And then there's a load of other stuff, and I'm deliberately calling it stuff, or stuff as I think French people would say, which looks complicated, but actually from a computational viewpoint really isn't, because it's all just local in space. So once, okay, you need to know what the gradient tensor is here, but once you've calculated that at any grid point, in terms of the sigma dynamics, it just says at any point in space, if you know what a sigma is there, you just update that sigma. So what we're going to do then, so this code, as usual, where you have a time derivative, is a time stepping code, and at each time step there are going to be two substeps. The first is that for some fixed value of sigma, which you've just found at the end of the previous time step, you keep that fixed, and then you ask, given that that's then just a source term on the end of the Stokes equation, given that you know that source term, what you want to do then is calculate the velocity field. You might incidentally also want to know the pressure field. I generally often don't, but you can find that if you want to as a byproduct. Given that velocity field, you then solve this sector here for a fixed value of that velocity field. You then have to update the viscoelastic stress sigma. And I'm going to describe these methods, so I'm cheating a little bit. I'm not telling, because actually channels are much more of a faff to do than periodic domains, but the basic concepts are really not very much more difficult. But everything I'm going to say here is for periodic domains, and I'll give you some references later on for how to do this in channels. So let's do the Stokes sector first of all, this sector here. So, and I'm going to write now, given that we know what the stress is, you can take the divergence of it numerically. You can do that in real space or Fourier space if you want to. Either way, that's just a source term, and I'm now going to call that f, which is a function of space. So given that, the equation that you need to solve is given f, how do you find all the rest of this? Now these equations now, they're linear and they're non-local, and so they're best solved in Fourier space, at least in a periodic domain. So to switch between real and Fourier space, maybe there are people here among you who know better packages for this, but I find the FFTW package very convenient for doing that. That's freely available. And having taken the Fourier transform, then the gradient term becomes IK. So you end up with these Fourier transformed equations now. So you've gone from V, P and F of being functions of R to now being modes in K. And the grad squared has become IK squared, grad has become IK, you've got IK there. So what you can do then is, so this here says that the divergence of the velocity must be 0. So now if you operate on this first equation with the divergence operator IK, you get ik.v here, so that term gets zapped. So then you have ik times p here, and ik.f there, which simply means that you can then calculate the pressure here by rearranging that equation. So just to summarize, incompressibility says that the divergence of the velocity has to be 0. You operate on this first equation with ik, in other words, compute its divergence. That is therefore 0 because of this. You then have ik squared times the pressure and ik.f, which you can then rearrange to get the pressure in Fourier space. You then substitute the pressure back into here, and in doing so, you then have ik times all of that stuff. So you have something in, you have just f on its own here, you have f with lots of operators in front of it in this term here. So you then bring all the f stuff over to the right hand side and rearrange. That gives you the velocity at any mode k as a function of the forcing, the force f. In fact, it is a force because it's the divergence of a stress. So this tensor here that we've effectively just more or less derived, even though I haven't gone through every gory last detail, is called the Oseen tensor. And clearly here what we have is a time-stepping code because we're time-stepping viscoelastic dynamics, but of course there's nothing that knows about time in this operator here, so just once at the start of any run you can calculate that operator at each mode k and just store it and have done with it, and then you can just look it up at any time step. So that's just how to solve the Stokes sector, and it's just a bit of a pain in the neck because you have to impose the divergence of the velocity being 0 to then find out what the pressure must be, but you can do that very easily, at least in a biperiodic domain. So now you've found the velocity, and you can then go back to go to the second sub-step, which is at fixed now velocity, as you've just found, update the stress. And as I said, the equations both for active matter, continuum Q-type models and constitutive models of polymers very often have this kind of structure. So there's this advective term here, might call this a trilinear term, I think yesterday, the green term, and there's the blue term, which once you've computed, and you can do this either in real or Fourier space, IKV or grad V in real space, once you've got this is just, this is the symmetrized part of this velocity gradient tensor. This is just a local equation in sigma. So at any grid point, you can update sigma at that grid point, given sigma at that grid point. So there's nothing difficult about that, even though it looks to be the most complicated bit. There's then the spatial gradient term on the end with this little parameter little l, which looked like the classic bracket squared operator that caused so much amusement yesterday. That's a diffusive term, so that's a little bit more of a headache. So this is a tensorial equation, but actually the essence of what you need to do is captured in this scalar version of it, which is an advection reaction diffusion equation. So we've got three types of term. We've got the advective term, which is spatially non-local. I'm calling it quasi-linear here, advective terms. You've got the spatially non-local but linear diffusion term, and you've got the spatially local but often non-linear reactive terms, which is all of this stuff. So what we do then at this second sub-step of the dynamics is split up this operator and solve these three steps successively in turn. And I'm going to illustrate the methods for doing this, and again, there's no rocket science here. You can look this up. More or less any of this even would be in, I think, Numerical Recipes, the Press-Tukolsky book. I'm going to illustrate them in one spatial dimension, but this easily generalizes to more. Hello? Yes? It does, yeah. Yeah. Right, but once you've computed the velocity field at any grid point, it's true you have to use a spatial operator. If you do it in real space, you discretize that operator and find grad phi, or you do it in Fourier space and then convert back to real space. But once you have that at any grid point, there's then nothing non-local about the sigma part of the dynamics. And because we're keeping V fixed at this part of in this step, the sigma dynamics is then just local. Yeah. Okay, so I'm going to do this just in one spatial dimension, but as I said, there's nothing complicated about going to more spatial dimensions. The complications in going up dimensions, by the way, is if, generally speaking, if you're trying to do 3D flow in a channel and solve Stokes' equation, that is a bit of a headache, but I'll give references for how to do that at the end. All right, so first of all, so the general form of the equation I said is the green advection term, the blue nonlinear local term, and the red spatial diffusion term. And I've set lots of things equal to 1 here, but don't worry about that. So the spatially local nonlinear term is actually very easy. All you need to do at any grid point, so there's nothing that says the grid points talk to each other, so that at any grid point that's just an ordinary differential equation. Now ordinary differential equations is a problem that many of you will have done at undergrad level probably. There are many techniques for that. The most Mickey Mouse one is explicit Euler, where literally you say at any time, the next time step n+1, you can compute that field, that at any grid point you can compute the updated value compared to the previous one by saying that the time derivative is discretized thus, and then you then have maybe think a bit about whether you want to take that to be C of n or n+1, that's explicit versus implicit. The explicit Euler just takes the value of C at that time step as you're starting out. That's called explicit Euler, and in fact in many of our viscoelastic codes, certainly early on, we use that and it works fine, but it does need a small value of the time step, so that then becomes a bit of a cumbersome overhead on the computational cost. There are more sophisticated methods. Again, you can look those up in any standard numerical recipes book. For example, fourth order Runge-Kutta is what we tend to use now. That's a little bit more complicated to code up, but not very much more. Again, it's local at any space point, and the advantage of that is that you can use a really much larger value of the time step, so that you can gain about a decade in computational time with that. So that's that term. So that's the easiest in a sense. Excuse me. There's then the diffusion term, which you can do in real space if you want, and the algorithm there is usually called Crank-Nicholson. and in a channel you might do it in real space in that dimension and Fourier space in that dimension. Because I'm in biperiodic space here, I have the liberty of just saying, well, this is a diffusion equation effectively in a biperiodic domain. So of course you'd be nuts to do that in anything other than Fourier space. So if you take then a Fourier transform, you get this very simple equation. Now, don't use explicit Euler for that or you will have a disaster, because it just turns out that modes, you need then a very small time step for larger k values if you do that. So and that's not just a matter of accuracy, the whole thing will explode if you don't do that. So the way to get around that is to say, don't just use the value of c at the starter time step, but you need to take a bit of the information of the time step you're going to as well. An explicit method would have no c of n plus 1, and as I say, is a disaster with diffusion. The implicit method doesn't have any of c of n plus 1, and it has c, it doesn't have any of that, but has only that. And that's stable, but it's not quite as accurate as having both of these. So this is the method that, if you were doing it in real space, would be called Crank-Nicolson. In fact, it may even be called Crank-Nicolson in Fourier space. I'm just not sure about that. The time derivative is discretized as normal. So you here just have literally, now it's local in k-space rather than in real space. But again, you can step that. And I said you could do that by implicit Euler, but it's just not quite as accurate. So that's that. Then finally you've got the advection term. Now, back in the day when I had time to do coding, this is what I would have used, and I think some of my groups still do. Some of them actually do it instead in Fourier space, and we have carefully checked it against this. I'm not going to describe the Fourier space method. I'm going to talk about the real space method, and there's a bit of physics really that goes into this. Well, there's physics that goes into all of this, but what you're thinking about here is convecting along a field C under the influence of an imposed velocity vector v. So if you've discretized your grid here, now imagine your flux of v is going in this direction, and you say at any grid point, how do I discretize how do I calculate the derivative of c? Now, if you didn't have any background velocity in the system, the way you calculate the first derivative of a field C at this point here is to take its value here, subtract this, and divide by twice the grid step. That's not a good thing to do if you have a flux of velocity here, because there's a direction in which information is flowing. So at that grid point here, it can't know anything about what's going on here. So in other words, you compute the gradient using information only from here and here. If it's coming from this direction, you use this instead. Now, what you can just take a first order derivative here. So that's the origin of this max min v business. It's saying take the information only from the upwind direction, not from the downwind direction. This would look a lot simpler in the first order method, which would just be c at I plus 1 minus c at I over dx. This is the x coordinate and this is dx. You can use that, I think, but in the very first kind of 2D viscoelastic code I ever wrote, which was actually this instability of this interface between the bands. I remember doing this on a visit to Paris in a very hot summer in a very hot lab at ESPCI. I had a lovely time there, but I was tearing my hair out over writing this code in between having great chats with Armand and Patrick Tabeling and all those people. And I was using first order upwinding, and what I was finding is that there's a dispersion relation for the growth of these interfacial modes, and they should all have different eigenvalues. And what I was finding was that actually information was leaking at order 1 between all those modes with the first order upwinding method. And it took me, 2 weeks of trial and error to find out, well, a bit more educated than trial and error, but to find out that actually I needed to use that. I haven't found another instance since then in which the first order one has been dangerous, but nonetheless, just to be safe, we tend to use the third order one, which is that one there. So that's just looked up in any Posrakidis lists it, for example. I think my voice is really going to give out now. All right, so just to summarize then, we do a time-stepping algorithm. The spatially non-local nonlinear terms are handled in real space, non-local diffusive in Fourier space, advective using third order upwinding, Stokes sector using an Oseen tensor for biperiodic flow. If you want to do channel flow, the viscoelastic sector is really not much more difficult. Generally, you just use the real space methods like Crank-Nicolson for the diffusion term in this direction and the methods I've just described in this dimension. The slight headache is solving Stokes equation in a channel flow. you can't just use the Fourier method I've just described very easily. So what do we do there? So in 2 dimensions, so I described solving the Stokes equation using the Oseen tensor. In 2 dimensions, you can instead take the curl of it and define a quantity which is a stream function, which is the curl of the velocity. You then end up with a stream function equation, which you can solve in real space this way and Fourier space that way. That only works in 2D. To solve Stokes equation in 3D in a channel, what you need to use, or one method that you can use, is something called an influence matrix. And in fact, it's only very recently that I've forayed into doing 3D Stokes flow in a channel. And the book that I found the most useful for that was this one here, Spectral Methods for Incompressible Viscous Flow. And once you've got that influence matrix method in your head, actually, it ends up importing many of these other methods, but with just one extra step. So with that, I'll leave you with these references. The 2 I've tended to use are these, plus numerical recipes, plus various things online like FFTW and so on. All right, so finally, just to thank my various co-workers, super postdoc Ewan Hemingway and Ricard Matas Navarro, who were with me in Durham, and collaborators elsewhere on the active matter stuff, Mike Cates, Ramin, and Davide Maranduzzo in Edinburgh, and Tanny in Bristol, and Julia, who was here earlier on in Oxford. And thanks for funding to the EPSIC and the ERC. I've no time now to talk about extensional instabilities. If anyone wants to hear about that, I'd be happy to talk about that offline. So with that, I'll take any final further questions. You all want your dinner, don't you? So do I. Thank you very much.